Welcome all my dear student of TYBSc physics class. In previous lecture we have studied the symbols of depletion type and enhancement type MOSFET. We also studied applications of MOSFETs, then advantages of N channel MOSFET over P channel MOSFET. And last point is that we studied the handling precautions regarding MOSFET. Now here we are going to solve the problem, but before that I would like to cover one point, that is advantages of MOSFET over JFET. The advantages of MOSFET over JFETs are like this. First, MOSFET has a very high input as compared to JFET. First advantage of MOSFET over JFET regarding input impedance, and this is very simple, that as compared to JFET, MOSFET has very high input impedance. Second one, MOSFETs having low output impedance as compared to JFET. Okay. And now as compared to JFET, MOSFETs has high gain. This is very important. What I say, as compared to JFET, MOSFETs has very high gain. Now when we compare the size of MOSFET and JFET, it is found that MOSFET has very small size, longer life and very high efficiency as compared to JFET. Okay. The next one, MOSFETs avoid the risk of thermal runaway. This is very important advantage of MOSFET over JFET. Then next one is that MOSFET has very high frequency runaway. MOSFETs has very high frequency runaway as compared to JFET. And last one is that MOSFET is less noisy as compared to JFET. These are the advantages of MOSFET over JFET. Now we are going to compare the difference between JFET and MOSFET. We are going to discuss four important points regarding the difference between JFET and MOSFET. First one is that when we compare JFET with MOSFET, it is found that JFET has 2 p-n junction, whereas MOSFET is having 1 p-n junction. Remember that JFET has 2 p-n junction, whereas MOSFET has only 1 p-n junction. Second important point of comparison, JFET has input impedance. JFET has input impedance. Now MOSFET has very high input impedance. JFET has high input impedance, but MOSFET has very high input impedance as compared to JFET. Okay. The next point, JFET, in case of JFET, JFET does not form the capacitor at the channel, whereas MOSFET forms the capacitor between channel and gate. This is very important. What I say, JFET does not form the capacitor at the channel, whereas MOSFET forms the capacitor between channel and gate. Next important point is that JFET is operated in both depletion mode. What I say? JFET is operated in both depletion mode, that is gate is reverse bias. Whereas in case of MOSFET, we can say that MOSFET is operated in both depletion mode and enhancement mode, that is gate is either positive or negative. And in case of JFET, gate is only has the reverse bias. And last one, in case of JFET, the gate terminal is directly taken from the channel. This is very important difference. What I say, in case of JFET, the gate terminal is directly taken from the channel, whereas in MOSFET, the gate terminal is taken out from the metallic layer deposited over the silicon dioxide layer, which is deposited over the channel. These 5 important points is very easy to understand, to remember. So, in this way, we completed the theoretical part of the chapter. Now we are going to see the problems regarding FET, MOSFET, JFET, etc. Now, first problem is regarding FET. Problem is like that. Problem is like this. When a reverse gate voltage, first problem. In this problem, reverse gate voltage, that is VGS is given, and that is 20 volt. What I say, when a reverse gate voltage 20 volt is applied to a FET, the gate current, that is ID, is of the order of 10⁻³ microampere. Then find the resistance between gate and source. I am going to tell you the problem is once again. The problem is regarding to FET, and when FET is reverse bias, when a reverse gate voltage of that FET is 20 volt is applied to a FET and the gate current is 10⁻³ microampere, then we have to find the resistance between gate and source. So, solution for this problem, this is the given data, this one and this one, and the important formula in order to calculate the gate to source resistance is RGS, resistance between gate to source. This is nothing but VGS upon ID. VGS is the reverse voltage applied to FET and ID is the drain current. Then substitute the value. VGS is 20 volt and ID is 10⁻³ microampere. Okay. Solve this, we will get 10⁻³ ampere, that is 20 into 10⁻³ microampere, and we have to convert it into ampere. When you compared it volt upon milliampere, that is unit will be in ohm, and when you calculate this, you will get 2 into 10⁻⁻10 ohm. Okay, this is a very simple formula. Then we are going to see, we are going to solve the next problem. Problem number 2. In problem number 2, when VGS of JFET changes from VGS of JFET changes from minus 2.2 volt to minus 2.1 volt. Then drain current rises from 1.1 milliampere to 1.4 milliampere. What I say, when VGS of JFET changes from minus 2.2 to minus 2.1 1 volt. At that time the drain current rises from 1.1 milliampere to 1.4 milliampere. And at this stage find the value of transconductance. So solution given the change in gate voltage. The change in gate voltage, that is delta VGS, delta VGS, and this is nothing but 0.1 volt. Then second point is given, the change in drain current, change in drain current. That is delta ID is equal to 1.4 milliampere to 1.1 milliampere, and that is 3 milliampere. So these two things are given, and we studied the formula for transconductance, and that is nothing but Gm is equal to, that is transconductance, change in drain current upon change in VGS. So substitute the values, change in rate 0.3 milliampere upon 0.1 volt. Solve this, we will get Gm is equal to simply 3 into 10 raised to minus 3, and the unit is mhos, MHOS, and symbol is like this, invert symbol of ohms, and reverse MHO, symbol for this is ohm, and symbol for this is this mho. Okay. Now I would like to tell you that you can solve the same problem with different values at your home. So, and that's supposed to be a homework. In first problem, instead of 15 volt, instead of 20 volt, consider the input, that is when a reverse gate voltage is 15 volt instead of 20 volt, and you can solve the problems once again. Okay. Now second problem, in this second problem you can solve the same problem by changing the value. If we consider the value of this current is minus 4.1 to 40, minus 4.1 to 4.0 milliampere. Or take the change 4.1 to minus 4.1 to 4.0 volt. Suppose this is the way. Instead of this, you can take this input, and instead of this current, you can take the current as 2.0 microampere to from 2.1, okay, or 2.3, So the difference is 0.2, and here the difference is 1. So 0.1 and 0.2, 0.1 milliampere, 0.2 volt. You can solve this problem once again. Now next problem. In next problem, Again, the problem is related to JFET. The JFET has pinch of voltage given. Pinch of voltage, that is Vp, is equal to, suppose 5 volt is given. The JFET has pinch of voltage 5 volt and ID, yes, drain saturation current is 100 milliampere. These two things are given and you have to find out ohmic resistance, and after then you have to find out the gate source cutoff voltage. So first of all, ohmic resistance, that is RDS, and formula for this ohmic resistance RDS is equal to Vp upon IDSS. Okay, substitute the value, Vp 5 volt and IDSS 100 into 10 raised to minus 3 ampere. Milliampere is given and substitute the value in ampere. So solve this, you will get RDS is equal to 50 ohm. And when this RDS, that is ohmic resistance, is 50 ohm when pinch of voltage is 5 and drain saturation current is 100 milliampere, at that time the pinch of voltage is 5, and for that pinch of voltage 5, the gate source cutoff voltage is what? Minus 5. VGS delta VGS off is equal to minus 5 volt. Okay, this is very important because JFET is always works in reverse bias. Now next problem. Okay, you can solve the same problem at your home by taking the pinch of voltage 6 volt instead of 5 volt and solve the problem once again. Okay. Now the next problem. In next problem, we have to find out 2 to 3 factors. That is, in next problem, we have to find out RD, that is AC drain resistance. Then we have to find out GM, that is transconductance, and then from these two we have to find out amplification factor mu. But listen the problem carefully. For a JFET, when VDS changes from VDS, that is VDS changes from, that is delta VDS, we have to find out first delta VDS, change in delta VDS, and initial and final values are given, and from that initial and final value we can calculate the change in value. So 14 volt. Here in problem the sentence is like this: for a JFET when VDS changes from 7 volt to 14 volt, that is 14 volt minus 7 volt is equal to 7 volt. This is the change in drain to source voltage. The next thing is given. At the same time the current ID changes from, that is change in drain current, that is delta ID, and this change in current is given from 10.20 milliampere to 10 ampere to 10 milliampere to 10.20, that is we have to take the difference like this, and this is nothing but 0.2 milliampere. This is the given data. Listen the problem carefully. For a jet when VDH changes from 7 volt to 14 volt, at the time drain current changes from 10 volt to 10.20 volt. Okay. Now when gate voltage changes from, that is delta VGS, gate voltage changes from 0.0, sorry, here when this type of changes takes place, at that time VGS is equal to 0. And when VGS is changes from 0 volt to 0.3 volt, 0 volt to 0.3 volt, then drain current changes from drain current changes from 10.20 milliampere to 9.60 milliampere. Okay. And this change is at constant VDS. And in this case, we have to find out the AC drain resistance, then transconductance, and then amplification factor. So, we are going to find out one by one. Solution first. Firstly, we have to find, we can see that with VGS constant, the increase in VDS is 14 volt minus 7 volt, because current is increased from 7 volt to 14 volt. So, increase in volt is 7 volt. The change in current, drain current, that is ID, is equal to 10.22 minus 10 is equal to 2 milliampere. So, from these two, we have AC drain resistance, that is RD is equal to simply VDS, change in VDS upon change in ID. Substitute the value 7 volt upon 0.2 milliampere. Okay. So, convert it into ampere. When 0.2 milliampere is given and when we want to convert it ampere, then we have to multiply by 3, and this is in ampere. Solve this by using calculator. You will get RD is equal to 35 ohm. This is RD. Now, when you are having the change in VGS, okay, VDS is constant. With VDS constant at 14 volt, the change in drain current ID is given like this. That is, this is equal to 10.20 minus 9.60 is nothing but 0.6 milliampere. This is change in ID. Then, and what is change in VGS? VGS is 0.3 volt minus 0 volt is 0.3 volt. So, by using these two values, this and this, transconductance GM is equal to simply change in drain current upon change in reverse gas voltage. Substitute the value 0.6 milliampere upon 0.3 volt, or 0.6 into 10 raised to minus 3 ampere upon 0.3 volt. Solve this, you will get 2 into 10 raised to minus 3 mhos. Okay. This is the GM, transconductance. And we know that amplification factor mu is equal to RD into GM. So, substitute the value, RD is equal to 35 ohm into 10 raised to 2 into 10 raised to minus 3 ohm. Sorry, this is 35 into 3 ohm. 35 into 10 raised to 3 ohm. Okay. So, substitute here 35 into 10 raised to 3 ohm into 2 into 10 raised to minus 3 mho. So this is cancelled with this and we have 70. There is no unit. Amplification factor is 70%. In this way, we completed whole chapter in detail.